Welcome back. In this last lecture, we developed the non-dimensional form or the normalized form of the equations governing the fluid flow and determined that the three named pi numbers, Euler number, Froude number and Reynolds number, control the similitude. In today's lecture, we will try to develop an understanding of the physical significance of these three main pi numbers of fluid mechanics. This is the equation that we developed for incompressible, steady, viscous flow of a fluid past a body with a uniform velocity V0 far upstream and the pressure P0 far upstream. When we normalize the equation, we got this form where we had made the coefficient of the inertial term as 1. The number rho V0 square by P0 is termed as the Euler number. The number V0 divided by under root GD is termed as the Froude number, and rho V0 d by mu as Reynolds number and is abbreviated by Re. Let's first talk about the Euler number. Note that it is not the pressure that appears in the governing equation, but its gradient. Therefore, all pressures may be measured with P0 as the datum. That is, we worked with differences in pressure rather than the pressure itself. We can work with the gauge pressure Pg defined as P minus P0. This is the pressure difference that requires a characteristic pressure difference for normalization, or that we need to know the pressure at some other point in the flow field. However, since no other pressure is specified in the problem, let's assume that the characteristic pressure difference is delta P0 as yet unknown. We'll discuss about what should the value of delta P0 be later. With this, the equation changes to this equation. V star dot del star V star is equal to 1 over Euler number delta star Pg star, the gauge pressure star, minus 1 over Froude number squared Ka, the unit vector in the z direction, plus 1 over Re, the Reynolds number, times delta star squared V star. And the pressure boundary condition becomes Pg star tends to 0 on Z star is equal to 0 as X star tends to infinity or minus infinity. P0 no longer appears in the mathematical equation of the problem and therefore is not a uniquity parameter. If the pressure forces within a flow field are to be significant, that is, they are not to be negligible, the pressure flow terms in this equation should be of the same order as the inertial term. So, this term must be of the same order as this term. The coefficient of this is 1. So, this coefficient should also be of order 1. This is possible if the characteristic pressure difference delta P0 is of the same order as rho V0 squared. So, this equation, in this, it is customary to set delta P0 as 1/2 rho V0 squared. What is the significance of this? You recall from Bernoulli equation, 1/2 rho V0 square is the pressure difference between the stagnation pressure and the static pressure in incompressible flow. So, that pressure difference, which is also known as the dynamic pressure of the flow, is taken as the characteristic pressure difference. And with this, the coefficient of the pressure term becomes minus 1/2, and this is the resulting equation. Notice that in this equation, the Euler number has disappeared, so that we can write the functional form of the velocity, the non-dimensional normalized velocity, as function of x star, the independent normalized variable, and gd by v naught square and mu by rho v naught d, the two groups of parameter, and of course the non-dimensional geometry. Wherever two pressures are specified in the problem, a characteristic pressure difference is defined by these two, and we can no longer set this to be rho v naught square by 2. The two given pressure in a problem would define the characteristic pressure difference. One such case is the flow of liquids with cavitation. Cavitation is a phenomenon where the liquid boils. When the pressure in a flow field of liquid drops below the vapor pressure of that liquid, then the vapors are formed and they result in vapor bubbles. If the vapor pressure at the temperature of the flow is P sub V, then P naught minus PV is a characteristic pressure difference that should be used to normalize the pressure difference. We've shown here a converging diverging channel with a liquid flowing through this. As the flow accelerates in the converging portion, the pressure drops, and that pressure drops if it is large enough so that the pressure becomes lower than the vapor pressure of liquid, then the vapor bubble would form, they would grow, and as this moves in the diverging portion, there would be an increasing pressure, and this would tend to make the vapor bubble collapse. This picture shows the vapor trail in a propeller of a ship. These are water vapors, trails that you see. The pressures at the tip of the blades is very low, below the cavitation pressure, and the vapor bubbles so form a nice beautiful picture as seen here. Thus, the pressure difference P naught minus PV forms an independent characteristic pressure difference, and Euler number has to be defined now as EU is equal to rho V naught square divided by P naught minus delta P. We can no longer take 1/2 rho V naught square as the characteristic pressure difference. Now, let's talk about the Froude number. Froude number is defined as V naught divided by under root GD. It is possible in some cases to redefine the problem in such a manner that the Froude number similarity can also be eliminated as a modeling requirement. We introduce a new variable script P defined as script P is equal to P plus rho GZ minus P naught. It may be noted that script P is defined to have a constant value throughout a stationary fluid. For example, if we have a fluid in this region, the pressure varies like this. This broken line shows the plot of the gauge pressure, P minus P naught, increasing with the depth in the fluid. If we subtract from this the value of rho GZ and formulate the variable P minus P dot plus rho GZ, we observe this to be constant. Thus, in a stationary fluid, the pressure P minus P naught plus rho Gz is constant. This is why this is termed as non-gravitational gauge pressure. With this value of script P, we can write P minus P naught as script P minus rho Gz. And if we take the divergence of this with a negative sign, minus del P minus P naught becomes minus del script P plus rho Gk. On normalizing the pressure difference by using delta P naught and by length by d, we get this equation. Now here you notice these two terms become this. And we can write V star dot del star V star is equal to minus delta P naught divided by rho V naught square delta star script P star plus mu divided by rho V naught d into delta star squared V star. Notice that the gravity term has been absorbed in this term which represents non-dimensionalized pressure, non-dimensional modified pressure, non-gravitational pressure. And we see that the Froude number has disappeared from the equation completely. This is the equivalent equation that we obtained in the last slide. And here P has been normalized to P star using delta P naught. The pressure condition is now changed to P star tends to 0 as Z star is equal to 0 as X star tends to minus infinity. Thus it is seen that the Froude number does not appear in the problem statement at all, and only Reynolds number and Euler number have to be matched. If in addition the flow conditions are such that only one pressure P naught is specified in the problem statement, then we can use rho V naught square by 2 as the characteristic pressure difference. This condition would be obtained in flows where there is no cavitation. Let's consider the application of this to problem in aerodynamics. We have an aerofoil at an angle of attack and we want to define or to determine the pressure distribution on the surface of the aerofoil. We can define a non-dimensional pressure coefficient Cp as the pressure difference P minus P naught, the gauge pressure, divided by 1/2 rho V naught square. We can use that as a characteristic pressure difference because cavitation is not involved in problems of aerodynamics. And this dependent variable should be a function of independent variable x star, the location on the surface of the aerofoil, and the parameter Re, Reynolds number, because Froude number as well as Euler number would not occur. And this will also depend upon alpha, the angle of attack, and the geometry of the aerofoil. Dependent parameter like the pitching moment coefficient, which is defined as the pitching moment per unit length of the aerofoil divided by 1/2 rho V naught square times the chord, is equal to the function of Reynolds number, alpha, and geometry. Obviously, since this is a dependent parameter, it does not depend upon the independent variable. This curve shows the plot of Cm versus the angle of attack alpha for various values of Reynolds number. It depends only on Reynolds number and not on the individual quantities involved within the Reynolds number. That is rho, mu, length, and velocity of the flow. From the independent parameters, we can determine the value of the Reynolds number and use the appropriate curve to find out the pitching moment variation with the angle of attack alpha. Let's discuss further about the Froude number. We have said that by defining the non-dimensional, non-gravitational pressure difference, we can get rid of the Froude number in the problem. However, this simplification is not always possible. For examples, in problems involving a free surface of a liquid, the shape of which changes with the motion, we cannot make the problem independent of the Froude number. At the free surface, which is given as z is equal to zf, a function of x, this free surface between the liquid and the air, for example, on the surface of a sea, the pressure is atmospheric everywhere. So at different values of z as a function of x, the pressure is constant atmospheric. If this be so, and we introduce the non-gravitational pressure difference Pg as P plus rho Gz minus P naught, the pressure boundary condition now modifies to script Pg is equal to rho G Zf at Z is equal to Zf's, which on non-dimensional gives you Pg star as rho GL divided by delta P naught Zf star at Z star is equal to Zf star. Now, the gravity and consequently the Froude number appear in the boundary conditions, so that the boundary conditions becomes P star is equal to Euler number divided by Froude number square at Z star is equal to Zf star, the free surface. Thus, though the Froude number vanishes in the equation of motion, the Froude number Fr appears in the boundary conditions and needs to be matched for similarity. Such conditions occur, for example, in the motion of ships and other vessels close to the surface of oceans. Similarly, Froude numbers in models must be same as Froude numbers in the prototypes in flows over dams, weirs, and open channels, where free surface is important. However, Froude number may be ignored as a similarity requirement for submarines operating at large depths. Then the presence of the free surface is far away and we can neglect it. In wave drag on ships, the drag coefficient CD, defined as drag divided by 1/2 rho v naught square into area, is now a function of Froude number, Reynolds number, non-dimensional geometry. So wave drag depends upon Froude number and Reynolds number. We can show that the dependence on Reynolds number is rather low. So the drag coefficient is a function of Froude number and the geometry. Here we have drag coefficients. On this side is Froude number, and these various curves are for various geometry. Geometry is measured by the displaced volume divided by the length cubed, and the length here is the draft of the ship. So the wave drag changes with Froude number and also with the geometry. Let's summarize the rules of thumb that we obtained so far for similarity. For a flow situation where there is no free surface but there is cavitation, for example, in poorly designed pumps where the cavitation occurs, in siphons and in torpedoes which operate at quite a bit of depth, we need to match the Euler number and Reynolds number only. The Froude number is not important because we are operating away from the free surface. However, the dependence on Reynolds number is rather weak, and the most important modeling rule is to match the Euler number. In the second flow situation that we discussed, we have free surfaces but no cavitation, like in ships, dams, harbors, offshore platforms, etc. Since there is a free surface, Froude number is important. Since there is no cavitation, Euler number is not important. And so we should match Reynolds number and Froude number. Here again, in most cases, the dependence on Reynolds number is rather weak. And so the most important modeling rule is the matching of Froude number. The third case that we discussed, there is no free surface, there is no cavitation. Deep submarines, airplanes, enclosed closed pipes, etc. Neither the Euler number nor the Froude number are important, and we need to match only the Reynolds number. We will see later that if the Reynolds number is very high, the dependence on Reynolds number also becomes unimportant, and the flow does not depend upon any of these parameters. It depends only on the geometry. The last case that we discuss is that we have free surface, we have cavitation, like in high-speed ships or torpedoes operating very close to the surface. All the three numbers, Euler numbers, Reynolds number, and Froude number, need to be matched. Thank you.